let me start by saying I think that you guys have a pretty good handle on what we've been doing so far, and so I am letting that help me in interpreting your solutions. The knowledge portions, there were a few points missed there, but there was nothing really significant lost there. You were both perfect on problem one of the small problems. Problem 2 through 6, which actually deal with what we are starting on in this chapter. It's taking the solution, right? What we're doing is how we get to that in this chapter. Threw you guys for a loop, both of you. And so let's just look at doing those. And then after we do those, then we'll start in with how we got to this solution. So I thought I was doing you a favor by choosing a sinusoid wave function. I thought that would make life easier for you. But in looking at your solutions, it was clear that the Gaussian is what you're comfortable with. So let's start with something that's not required. Here's the wave. Oh, come on. Here's the wave function, right? So let's just graph what that wave function looks like. Now we have it's 0 everywhere except for between 0 and L. And since it's a sinusoid and it's going from x equals 0 to x equals L, that means we're going to go from an angle of 0 to an angle of 4 pi. That's 2 cycles of the sinusoid. So the wave function, oh goodness, I did not give myself enough space there. That's also interesting, but that's a different problem. So let's mark this higher, 0 and L there. So our wave function is, of course, 0. That's perfect. 0 outside of that range. And then a sine wave goes. And so it should be doing, that's 1.5 cycles. 2 cycles. So that's what our wave function looks like. So I can go straight to problem 4 by squaring that. Problem 4 was just squaring that because the key here is probability density is psi mod squared. Since this is all real, psi mod squared is just that squared. So if I square this for problem 4, I should have had something that goes like this. Like that. And so where is it most probable? Where it's most probable where you have the highest probability. And so you have 4 locations of equally high probability. So those 4 locations are where it's most probable. And then you can just look at this picture and determine, well, the probability is symmetrical. So find the expectation value. If I find the average from a whole bunch of measurements with this probability distribution, it's going to be at the center. So you had to calculate that beforehand. And like I was telling one student, if you calculate problem 3 incorrectly and you mark 3 correctly on problem 4, I would take that as correct rather than marking you off twice for the same thing. But here's the most probable, the expectation value. And what's the probability of being at the expectation value? 0, right. Probability is 0 there. So even though it's the average, and we call it the expectation value, you have to differentiate. That's never going to happen. It's just what the average is going to be. Now, going to problem 2, find the value A. Both of you identified this means I need to normalize it. So I have normalization condition 1 equals integral of psi star psi dx. Do remember to put the dx's there. One of you forgot to put dx's a lot of places. This needs to be over all space, which for this problem was just going from 0 to L. Said to make A real and constant, so I can just put A squared out front. Sine squared of 4 pi x over L dx. Now, this requires just a u substitution. Change color. Let u equal 4 pi x over L. So du is equal to 4 pi over L dx. Therefore, dx is equal to L over 4 pi du. And I have 1 equals a squared integral from 0. And let's just put it, instead of L for my limit, I'm going to put 4 pi. And I did see what you had done, and it was right.
Because I just put in the u's.
Yeah, you put it back in terms of x, and I was expecting it in terms of u. So 4 pi L over L, so the L over L's cancel. It's just 0 to 4 pi of L over 4 pi sine squared u du. And then we look at our integral table, which I put a bunch of blank pages in here. So sine squared x dx is 1/2 x minus 1/4 pi minus 1/4 sine of 2x. Now I'm going to save us some time here. Obviously, I expected you to do this fully on your solution. But since I'm going to put in the upper and lower limits, that's going to subtract out because that's a constant. And sine of 2 times 4 pi, that's sine of 8 pi. Sine of any integer multiple of pi is 0. So sine of 8 pi is going to be 0. And likewise, when I put in my lower limit of 0, sine of 0 is 0. So this is going to be 0 for both terms, and this is going to subtract out. So the only thing that I really have to worry about is the 1/2 x. Now, like I said, in your actual solution, you would need to write these out. So it was 1/2 x, right? So now putting this, notice the 4 pi's will cancel, and I have 1 is equal to a squared L over 2. Therefore, a squared is equal to 2 over L, which leads me to a is equal to plus or minus the square root of 2 over L. Now, if you just chose the positive root, I did not mark you off. Because what we really care about is having a and a. So that's the first normalization. So now that we have a, as I go through the problems, I'm generally just going to put a still because it's quicker to write than square root of 2 over L. But now that we have that, we can go on to what's the expectation value for position. If you don't have a, you can't get the expectation value. So expectation value, now to make sure, okay, what do I do? There it is. When you do expectation values, you always should start with this. Once again, I put the limit 0 to L because that's the extent of our wave function. You should have the x operator between psi star and psi. If the function is a function of the operator, then you'll get your eigenvalue that you can move around. It's called the eigenvalue. But you should start this way. And so in our case, that's going to be integral from 0 to L of a squared out front. And I'm going to have sine of 4 pi x over L times x times sine of 4 pi x over L dx, which can be simplified to and we use exactly the same u substitution as we did before. except for now I'm going to have substitute in for x as well. And so my integral becomes now, let me emphasize here, this L over 4 pi squared comes because I had an x, which has this, times a dx, which has that.
So you don't need to do an integration by parts?
No. I was not sure when you mentioned that. I was not sure, and I looked at your work and saw, where you went. So now we have this, and once again, we look up this integral in that table. So u sine squared u du is going to be this one here. Whoops, nope, that's single sine. There's cosine squared, there's sine squared. This one here. Now in this case, once again, we're going to have the sine terms. Sine of 0 and sine of 8 pi are both going to be 0. So those I don't have to worry about because they're going to be 0 both upper and lower limits. Cosine of 2x, that's going to be cosine of 4 pi and cosine of 0. Cosine of 4 pi and cosine of 0 are both 1. And so I have to worry about this factor except for it's going to be minus 1/8 for the upper and lower limits because the cosine is going to be positive 1 in both cases. So that one is going to subtract out again. And so I have the 1/4 x squared that I'm going to have to worry about. And as I emphasized before, I would expect you in your solution to show the full 9 yards. Minus 0 if you want to put the lower limit there. So there is our answer for the expectation value and position, but we have a lot of simplifying to do. First thing to do is to cancel out the 4 pi's, 4 pi squared and 4 pi quantity squared. Since a was square root of 2 over L, a squared is 2 over L. So cancel one of the L's, cancel a 2 is L over 2. Now, by the way, going back to this previous one, whoops, where's the previous one? Yeah, right here. One of you had left in the sine of 8 pi. Well, since sine of 8 pi is 0, that was still correct, right? One must have had the calculator in degrees because calculated for sine of 8 pi and didn't get 0. And yeah, when I was grading that, I was going to remind you, when we're doing quantum physics, I don't think there's ever going to be a case where we talk about degrees. Anytime we use trig, it's going to be in radians, which are the natural unit, the one that doesn't require a conversion factor. So if there's ever a question in this class, radians. Okay, so we have the expectation value. We have of course, the normalization constant. We've made the graph. We only have one left. Is this a wave function of the momentum operator? Why or why not? So is it a wave function of the momentum operator? Let's see, I'm out of space. So the way we test to see if it's a wave function of the momentum operator is if P operator gives us a P that is times psi. Well, our P operator is h bar over I d dx. Therefore, P operator acting on a sine of 4 pi x over L is equal to h bar over I times a d dx of sine of 4 pi x over L. Doing that derivative of sine, it's going to give us cosine of the same argument times the derivative of the inside. So h bar over I a, and then I'll have the derivative of the inside is 4 pi over L cosine of 4 pi x over L. And there are two very strong reasons to say no. What are those two strong reasons?
There's an imaginary part to it, not to the eigenvalue. It's not
Yep.
real. And then also it changes the original eigenstate.
I'm going to put complex just because if there was somebody who didn't know what we were talking about and they read this, it would look even stupider to say it's not real, it's imaginary. So saying it's not real, it's complex, at least looks a little more meaningful. It's complex, it's actually imaginary is truthful. Complex really isn't, because complex means real and imaginary. But I couldn't write it, okay? And then the second reason is exactly what you said, doesn't return the same function. You went from a sine to a cosine. There's no way to rectify that. So that one there, no, it's not because of those two reasons. 5, 2, 3, 4. Last, the bonus question, what's the kinetic energy of this particle? Well, using this relationship, we should have the kinetic energy operator acting on psi is equal to, and I'm going to put Ke just for your comfort, psi. And so the kinetic energy operator is minus h bar squared over 2m d second dx squared of psi. Take the second derivative of sine, that's going to give you minus sine, times the derivative of the inside twice, so I have to have the 4 pi over L quantity squared. So that thing in parentheses is the second derivative. And so now we put this together and we say, okay, oh, what did Richard forget? The A. I forgot the A above too. Oh, no, I didn't. I had the A there. It's just here I forgot it. So I'm going to have is equal to minus and a minus makes a plus. H bar squared over 2m times 4 pi over L quantity squared times A sine 4 pi over Lx, which is 1 over 2m parentheses h bar 4 pi over L quantity squared psi. So what's our kinetic energy then? It must be by matching up. That's the kinetic energy. So I obviously ran through this quickly. One thing you notice is, well, once you know how to do these, they do go quick. But if you don't know how to do them, which of course, why else would you have them on the test except for something that you didn't know how to do that you're just learning? It takes long. But do you have questions about how these solutions work? No. Okay, so can you close my office door? Okay. So if I were to give you the test again, you're pretty confident you'd be able to crush it now? Okay, because I think that you guys were ready, and I just threw you for a loop because you had done everything with Gaussians and you were expecting something Gaussianish. So I didn't use as much paper as I thought I would here. Let's get to the next thing. particle in a box. Particle in a box is your first quantum physics problem every time. And so we're going to start with the Schrodinger equation, and then we're going to apply the Schrodinger equation to a quasi-real situation. So here's the Schrodinger equation in all of its glory. Now notice the Schrodinger equation, it now has a capital psi here. I've been using lowercase, whoops. What's missing from this Schrodinger equation, friends? Forgot to write that psi there. This Schrodinger equation has two variables, time and position. Now, if you want to get all technical-like, we should have three-dimensional position. And in fact, when we do the hydrogen atom, we have to be all technical-like and have that three-dimensional position. So this is one-dimensional because you know what? You got to start simple and work your way up, not start hard and work your way down. So we have two variables here, position and time. And the first thing I want to do is to get down to one variable. And you might say, but that's impossible. And it might be impossible except for the special case, which is almost always the case. It's always the case for our class if V is a function only of X. If the potential energy only depends on position and not time. Does that make sense? For the most part, yes. If we talk about gravitational potential energy, it only depends on the elevation. At this elevation, the gravitational potential energy is not going to change over time. If you change elevation with time, sure, it's changing, but that's because the elevation changed, not because the time changed. So in everything we're going to do in this class, our potential energy is going to be a function of position. So I can write this equation out as IH bar d psi of x comma t dt equals minus h bar squared over 2m d second psi of x comma t dx squared plus v of x, whoops, capital shouldn't have that, psi of x comma t. Now I've been very explicit where there's x's and where there's t's. And you notice those are partial derivatives. Partial derivative with respect to time means it's treating x as a constant. It's only taking a derivative of the time part. Partial derivative with respect to x is treating time as a constant. It's only taking a derivative of the time part. So what we can do is we can let psi of x comma t equal psi of x phi of t. So I said it's going to be the product of two functions. One function that's only a function of position and one function that's only a function of time. So that you multiply the two together and you have a function of x and t. And so notice I changed from a capital psi here to a lowercase psi. That's why I tilted it a little just to try to make sure that they're not the same psi. This thing gets confusing to me. We have multiple ways of writing psi. And we're going to mean different things. When we write it like this, we're going to mean the complete wave function. And when we write it like this, it's going to mean a solution that's not the complete. We'll see more about it later. So if I make that substitution and put that into my Schrodinger equation, I'm going to have, I want to change back to red. I'm going to have IH bar. Since the partial derivative with respect to time is not going to affect the position variable. Okay, that's not right. Actually, let me use color coding here. So there I've written in red all of the position dependent stuff, and in blue all of the time dependent stuff. And now the trick we do is we say, okay, let's try doing something weird. Let's see if we can separate variables. And you might notice that there is a little mathematical problem in this, but we do it anyway. What's the little mathematical problem in what I just did?
Psi can be 0.
Psi can be 0. Psi can be 0, and so this could be division by 0 thing. So it's something we're going to have to, take some mind into. But in general, psi is not going to be 0. And so for the general time, it's correct. And it's just you have instances where it's not. And so in this case, whoops, crossed out the wrong one there. I now can write this as, going back to my color coding, one more thing. What is special about this equation? Which hopefully is clear because of my color coding.
And all the time dependent stuff is on the left. Position on the right.
Right. So what this means is I now have this and this that have to be constants. They have to be constant because I can change time and only this one changes, this one doesn't change. Or I can change position and keep time constant, only this side changes and not this. Both of them are going to have to be constant for that to be true. And so we, not at all arbitrarily, set this equal to E. And so this gives us two equations in the end. We have IH bar, I should go back to my color coding. So there's one equation, that's the time variation, solutions of the Schrodinger equation, which knows it doesn't depend on the potential. That's the same for every stinking problem you ever do. Since it's the same for every stinking problem you ever do, we're going to solve it once and then understand that every solution we get for the position part is going to be multiplied by that. This here, it doesn't have the potential energy function V in it at all. It's going to be the same for every single quantum physics problem you ever do. What you ever do. You get to higher levels, you might find some cases where you don't. So what we're going to do is we're going to find the solution for this find phi as a function of t. And then we just know for every problem we ever do, we'll find our solution for the spatial part, and then we multiply it by the solution for the time part to get our complete solution. So the solution for this is going to be the same for every problem. We're never going to work it again and again and again because that would be very boring. So we're going to do it today, and that'll be the end of it. But we have to be aware that it's always part of the problem. It's just always there. The second equation then is going to be minus h bar squared over 2m d second psi of x dx squared plus v of x psi of x equals e psi of x. So we have two equations now. We have the time part, space independent, if you will, and then we have the time independent part. The time independent part, we always want to be very clear. That's the time independent Schrodinger equation. The one we started with up here is the time dependent Schrodinger equation, the one that's printed and missing the psi. That's the time dependent Schrodinger equation. What we have now are two different equations. One that is the time independent Schrodinger equation, which I'm going to put the box around because this is going to be the one that you use heavily. And then we have this one here that gives us the time solution for the Schrodinger equation. I'm emphasizing this because when I took quantum mechanics, I got really confused about the time dependent and the time independent Schrodinger equations. And I was like, they look so similar. There's a slight difference. What's the deal? And so this separation is an important thing just so you have clear what the deal is. Go ahead, Eric.
I'm not understanding. We're solving for phi t for the time dependent portion.
Yes.
And why does that always stay the same then?
Because it doesn't have the potential energy function. It doesn't matter what your situation is, that part is going to always look the same. The potential energy function is the only thing that's going to be changing from problem to problem to problem.
So you're saying the time dependent portion for any wave function that we're looking at, or for any part
for any yeah, it's going to be the same.
Okay.
And so we just find it once and we go from there. Now, note both of these depend on this constant energy. If the energy changes, well, the energy in your solution there changed, but it's still energy. Now, I have slides with this. Through some work that we just did, you can get here's the time independent one, and then the time dependent one. And we will start by solving this time dependent one. I'm sure on my next slide I have it, but I like to do the work before I get to the slide that has it on it, because it at least shows I know what I'm doing. You know, I can read slides. Look, hey, look, we can all read. So I want to solve this to find, you say phi, I say phi. To solve it for that time-dependent function. So this is, well, since we're doing simple, it's one of your simple differential equations. We have two variables, if you will. What would the two variables be in this function, or this equation?
Considering E to be a variable.
No, E is a constant.
So
Time and?
Function.
And the function phi, right. I asked you the question that seems simple because, yeah, it's a function. Is that a variable? As far as the differential equation is, yes. So when you have two variables in the differential equation, you want to separate, just like we already did, right? We separated the two functions. Now we're going to separate the variables. So I need to move all the ph's to one side and all the t's to the other. So I'm going to have d phi over phi. Notice I'm dropping this as a function of time here. D phi over phi is equal to E over I h bar dt. I multiply both sides by dt, so I get it in the numerator position. I divided both sides by phi, so it would not be with the dt. And so now the left side and the right side are independent. What's the next step once we have the variables separated? To what? Okay. I thought I heard you say tickle. And that just didn't make any sense to me at all. So we integrate. Yes, well, I mean, mathematicians might tickle a function. I don't know. So what's the integral of d phi over phi? We do need limits. So I'm putting phi initial to phi final. And for time, I'll put time initial equals 0. Right? Phi is not necessarily 0 when we start, but we can always set our timer to start at time equals 0. So let's do that to make life easy. To time final. When I'm all done, I'm going to drop the subscript f's. But I have to put them in there so I don't technically have my limit the same as my variable of integration. So this is going from phi 0 to phi final. What's the integral of E over I h bar dt? It's tough. I put in the limits already because it was going from 0 to t final. Now notice I moved the I from the denominator to the numerator, which introduced a minus sign as well.
Why did you do that?
Because we don't like to generally leave I in the denominator. It's a preference.
But you also don't like to have
A negative sign. I know. We're fighting preferences now. But in quantum physics, we're probably bad boys of science because we put I in the denominator often. But here we're not making mathematicians angry, and we put it in the numerator. Okay? Natural log of... When I put in the limits to the natural log, I have natural log of phi final minus natural log of phi initial. I can combine those into one natural log of phi final over phi initial. At this point, I will relax and let t final be phi at any, or phi final be phi at any time, and t final will be the t at that same time. And then I have one last step. How do I get rid of a natural log in a function? Yeah, the exponential, because that's the inverse function. And so I take the exponential of both sides here, and I'm going to have phi of t divided by phi 0 is equal to e to the minus I e t over h bar, or phi of t is equal to phi 0 e to the minus I e t over h bar. That is our time-dependent solution. Now, when you look at that, it may or may not ring a bell to you. That is a sinusoidal variation. E to the I something, e to the I theta, is equal to cosine theta plus I sine theta. So this is a sinusoidal variation. Notice it is complex, cosine plus I sine. So we're going to have a fundamental complex part, but you've actually already seen this in problems we did. We did problems that had a real solution, so it had this time part with it. But when we took the complex conjugate and multiplied them together, it dropped out. Okay, so that's the solution for the time part. Always that same solution, so we're not going to repeat it again. Now, that doesn't mean that on the next test you won't have to find the time solution once to show that you understand it. But we're not going to do it over and over and over and over. So, do you understand this time solution part now? Is it making, well, I was going to say, is it making more sense? Well, of course it should be making more, but do you understand it?
So what we'll do in practice is take this solution and multiply it by the energy. And to, like, how are we relating this to the position?
Okay, so what we're going to do in a real case is we're going to take the equation that I circled here in blue, and we're going to solve that to find the space-dependent solutions as well as the energies. And then we will combine them. Okay, so there's the solution we just did. Then we're going to combine them to say that our complete wave function is equal to, and let's just look at this here for now. This here is the spatial solution, the psi, times the time solution. Now, there is another part here that's important, but I want to go back and I'll come to it. And that is when we solve the time-independent Schrodinger equation, we're not going to get generally one solution. We're generally going to get multiple solutions. In one case, we'll get two. In most cases, we'll get an infinite number of solutions. And when you have an infinite number of solutions, it turns out each of those solutions corresponds to a different energy state. So you have this solution in this energy state, this solution in this energy state. And then when you ask, well, what is the actual wave function? The wave function must be a linear superposition. That is, it's some percentage in this state, and some percentage in this state, and some percentage in this state of all of them. Now, those percentages can be zero. It depends on how you set up your system. And so that's what the summation part of this equation is. We have this C is saying, if you take the mod square of that C, it's telling you what percentage the state is in state n. And so if you sum up C mod squareds for all n's, you'd better come to 1 again because you have to have it normalized. And so this is saying that we have a certain percentage in state 1 plus a certain percentage in state 2 plus a certain percentage in state 3. And this here is the complete wave function for state n.
For just that state?
Yes.
Okay. Where did the phi 0 go?
The phi 0 it's a constant.
Okay.
And so that's just coming out into that C. Yeah. Because we just have one constant in the end.
Okay.
So just to make sure, as a last step, we only have 5 minutes left to start the problem. So as the last statement on this, when I talk about the states, let's take this something you're both chemistry majors, right?
Yeah.
So something you as chemistry majors are comfortable with. If we have a hydrogen atom, we can have the electron in the n equals 1 state, where it has an energy, the atom has an energy of minus 13.6 electron volts. Or we can have it in the n equals 2 state, where we have an energy of minus 13.6 divided by 4, would you believe? Electron volts. Or we have in the n equals 3 state, which is minus 13.6 over 9, and so on, right? So we have by state. That's the state. And so the way this works is we would have n equals 1 was that minus 13.6 eV. And so the time dependent part would have, for the E sub n, it would have the minus 13.6 eV there. And then the psi sub 1 is the solution we're going to find if n equals 1. For the time independent. And then the C sub n is going to depend on how we set up our system. You can have a set of atoms that are, if it's at a high temperature, the likelihood of it being n equals 1 is very low. because collisions are causing them to go to excited states. So it depends on how you prepare the system, what the C sub n's are.
But you're able to find that out for that energy state before summing up all of the energy states?
Well, you are, so this here, the psi sub n, that's going to come from your potential energy function. And then the C sub n's are going to come from how you prepared the system.
All right. So, like, how would you know, though, what the probability is of it being in that state without?
Let's take it to something that's a good analog. I don't have it here anymore, thank goodness. My little stringed instrument, that I use for demonstrator physics. If I pluck it at the center, then I know that there is not a node at the center on that string. And so I know that I'm going to have all of my odd harmonics have a C sub n of 0. Or odd? No, even. All of the even harmonics can have C sub n of 0 if I plucked it at the center. Because by the way I plucked it, the way I prepared my system, I've made it so I can't have that. Now, to get the actual result, you actually do an integral. I pluck it if I know that I pulled it up to this displacement and at this location, I can do an integral and I can actually find all the C's based on me plucking it and it initially being a straight string going from there and there.
Okay.
So it's something, and we will be doing that. We will be doing the integral to calculate what the C sub n's are for a given preparation. Okay, 3 minutes. I'm only going to describe this and we won't start it.
Are we going to have the homework due tomorrow still?
No. It's not even shown on Moodle yet, is it?
Right, I don't
Okay.
think so.
Yeah. The reason for that is just like here, I had, the test was very similar and I reviewed the test and I didn't want you to, go and look, oh, look, there's the test questions. And so I hit everything from that segment. And I will be opening them up one at a time for that reason. So particle in a box or infinite square well, they mean the same thing. So I will say particle in a box because that's what I was taught when I was your age. What it means is you have a box, and the box, you can think of it as a real physical box. It's a quantum analogy to a real physical box. But this box has infinite walls. So remember, with potential energy's reference point is arbitrary. You can set the reference point wherever you want. So we choose to set the bottom of the box as 0 potential energy. And the walls go up at infinite height, so it's infinite potential energy to get outside of the box. Right, so if the particle is anywhere outside the box, it has infinite potential energy. What are the odds of that happening? 0, right? Your particle is not going to have infinite energy. So the particle is contained to be in the box. That's what we call a particle in the box. Infinite well, because it has walls that go up to infinity. So in this case, our potential energy function is written in 3 pieces. Minus infinity is less than x is less than 0. I'm just using less. I'm not using less than or equal. Some people will be technical on these things. In that case, the potential energy is infinite. So there's my potential energy function. I have 3 pieces. This is what you had for that problems 2 through 5 on the test. 2 through 6, I guess, is the bonus one. And so we didn't do the integrals from minus infinity to 0 because if your potential energy is infinite, the probability of it being there is 0, so psi was 0 in that region. We didn't do it from L to infinity for the same reason, because psi was 0. So technically, the solution that you had for that problem was and then what I gave you. Right? That's what the actual full solution was for that problem. And this is a solution to the particle in the box that we will figure out mañana. Notice, spend the rest of the class period solving the problem. How about we spend next class period solving the problem? Oh, I hate it when I do that. I had the button right here to stop.